You might have done all the analysis and design review in the world, but I can almost guarantee that the first time you go to assemble that system and try it out, it's probably going to have something wrong with it. So in this video, we're talking about testing. Now, if you want to become a trusted lead engineer, you're going to have to understand the different types of testing, when we apply each, and why it's important to do so. So let's get into it in this video. Welcome back to Engineering Aerospace with me, Eric Kane. Alright, in this video we're going to be talking about testing and the different types of tests that you might come across, as well as why we do each of these types of tests and what are the different levels that we can do them at. So if you're engineering a system, there's a variety of different reasons you might actually do testing. So of course some of the obvious ones are you have a list of requirements and you need to do verification to make sure that your system meets those requirements. Now this could be everything from just a simple avionics box. This could be structures where you're going to actually physically test the structure. Could be software. Testing is used all over the place in the engineering world, and there's good reason for it. And that's because the systems we design are complicated. They often don't do things the way we think they should. Sometimes our analysis might be wrong. Someone may have made an error somewhere in the process, and so we need to make sure that when we build something, design something, that it actually does what we intended it to do and does it properly. So if we talk about the different types of testing, we have kind of almost different levels, right? So we talked about qualification or verification testing, right? These are the kinds of tests that you would do when you're trying to make sure that everything meets requirements, right? These are very strict tests that are done. They have very explicit objectives, usually written out as part of the requirements set, and you're proving that you meet those requirements. Now that can be fairly straightforward in that it can tell you exactly how to set up a test because, the requirement is already outlined for you ahead of time. But there may be occasions where it's a little bit more vague as to what a requirement really meant, or perhaps, you can't prove it directly, you have to indirectly prove it. And so you may have to design a test around that. Now, if we kind of step things back to the beginning of like a program, if you were starting a project, there's kind of a different build-up approach that you might take with engineering testing. So qualification's really kind of at the very end of the process. So if we're starting a project new, chances are we're going to be doing more development level testing, right? So this is testing where we don't really know exactly how something's going to behave. This might be characterization tests where if I have an off-the-shelf piece of hardware, I need to bring it in and see how it actually operates, right? You can look at a spec sheet online, but that doesn't necessarily tell you how it's actually going to behave. Even if you get the manual, sometimes things don't behave the way you think they do based on the way you read it. So getting hardware in the lab and checking it out just to understand its behavior is what I consider characterization or familiarization testing. Now, I've done quite a bit of this when we do stuff in the labs where we get off-the-shelf hardware because it was already designed, but we just needed to understand how it operated and to make sure that when we developed the requirements for how that fit into the system, that it actually those requirements reflected the true behavior of the components we were including. Now, of course, if you're designing your own system, this might be we're just trying to understand subcomponents, or perhaps we're just trying to get a lay of the land and understand what's possible before we get too far into the design effort, right? So this is very early in the program phase. Now, kind of the next level up from that might be what I would consider risk reduction or kind of prototyping phase, right? So we're not just playing around with something, just trying to understand how it behaves. Here we're actually trying to prove something, right? Or buy down risk. Technologies get complicated, and so sometimes we think we know what's going to happen, but we haven't done it before, so we need to prove it. This kind of goes into some of the NASA technology readiness levels, TRL. A lot of those would be on kind of like the lower end of the TRL scale, where you're just trying to prove the technology works. Risk reduction might be if you have a big program where there's a lot of concern that some technology may not be available in time. It may not meet the performance you need. There may be some characteristics that perhaps it's going to be expensive if this thing doesn't do the way you think it will, and so we need to buy down the risk by doing that testing early in the program. And so sometimes you will do that early just to minimize that risk, mitigate it early, and there may be challenges which take time to overcome. And so the earlier you can get on those important ones, the better. Now, another type of test you might do is something like a performance test, right? So maybe you have a component or a box or something like that, or even a subsystem where you kind of, you play around with it, you understand it, but now we need to push its limits and understand where does it stop working. Maybe you want to run something as fast as possible, push a data bus to a limit, push a structure to a limit, something like that, right? So these are all different kinds of tests that you can do just to see if you're not certain what the answer is. Maybe you just want to go see what the performance envelope looks like, vary different parameters and see what the behavior is. So it's kind of similar to the characterization testing, but this is more numeric, more quantifiable versus qualitative. And so you're trying to prove out the limits and the behavior of the system in a more detailed manner. Now, of course, if you have one component, like a box like this, it's probably part of a much more complicated system. And so you want to do some testing where you hook this box up to the other boxes that it will be connected to and make sure that those components work the way they're supposed to as a system, or a subsystem. And so this is what we call integrated testing, right? So you're bringing the different pieces together and you're integrating them together. Now, this brings up a lot more complications that can happen because, even though you may have defined the interfaces up front, sometimes they don't behave the way you thought they did, or even during prior testing, the test wasn't set up properly. And so you need to get all these components together to make them actually operate the way they're supposed to. You will find issues where things just weren't wired the way you thought they were, or they behave when they're connected differently than expected. So this is a very important type of test. And so we do this a lot in the lab, and then eventually we might do this on a fully integrated vehicle, right? So if you're building an airplane or a spacecraft, rocket, whatever, you have to eventually get all these components together. And now the risk, of course, goes up, right? Because now I have more hardware, more expensive hardware, all connected together. And there's always a risk that I could break one of them if I, for example, plug something in the wrong port, or something behaved unexpectedly and damaged another component down the stream. So the risk level tends to go up, and this is why we tend to do kind of like a bottoms-up approach to doing testing. Now, there's also different types of testing between acceptance and qualification. Now, acceptance testing is more or less proving individual pieces of hardware have satisfied the design intent and they are built properly, whereas qualification testing is really more or less verifying the design is good. So you can think of qualified design as just proving out the design meets all of its requirements, and then acceptance is every time you build one of these, does it meet the design and does it satisfy those repetitive requirements that every piece of hardware needs to satisfy. If you're working in the FAA world or the aviation world, you may not hear qualification. It might be more certification. It's the same concept, right? Is you have a set of requirements the design must satisfy, and you prove that out through some sort of test program. So what are the major objectives for these different types of tests? Well, obviously, functional and behavioral testing, like characterization testing, you're trying to prove out what are the behaviors that the component does. Does it, when I send it this command, does it switch over to this mode or that mode? What are the voltage outputs that it creates? Perhaps if you're doing structural testing, what is the frequency of the structure? We're trying to understand, what it looks like. and understand perhaps we've got an aircraft and we're trying to do testing to see what the vibration environment looks like so that we can put equipment on it. And so you're just trying to understand some sort of functional behavior or performance parameters. Now, of course, you can do performance numbers where you're actually collecting much more detailed data, not so much, general behaviors or modes or those kinds of things, but more parametric measurements. So things like if I fly an aircraft, I'm going to see, how it behaves at, different Mach numbers and different altitudes and temperatures. And so I can build out a full performance envelope. Now, another common type of testing you're going to see is environmental testing. And again, this can be done at different levels, but a lot of times if you're working just at a component or hardware box level, you're going to do environmental testing to make sure that that component can survive whatever environment it's expected to see on board the vehicle. And then a lot of times we will do environmental testing of complete assemblies of the vehicle, whether that's an airplane or a spacecraft or whatever. You may put it in a chamber and test it, or put it out in the real world and test it. So, the different levels again start to come into play. Another reason that we'll do testing, particularly acceptance testing, is for quality control, right? So every time you build a piece of hardware, it may be copied off the same design, and that design was probably proven early on to be good, but just because I proved it to be good last time doesn't mean the next time I build it, it's going to be built the same. So a lot of times we'll do acceptance testing to make sure that the quality of each component coming off the production line satisfies requirements. And then, of course, we have the integrated functions, right? Trying to make sure that we do full operational testing of the vehicle. It meets not just all of its, kind of switchology and data flow requirements, but you may have to go check performance, and eventually you might have to take it out into an operational environment and verify it meets kind of all the even higher level objectives and requirements. So when we talk about testing levels, you can start at the bottom, right? You can almost think of it as a pyramid, a build-up approach, which is testing always kind of starts at the piece part component level. So if you think an electronics box, this might be something like resistors and capacitors and microchips, making sure that those components can survive and operate in the rated conditions that they're kind of certified for. And then you can kind of move up to sub-assemblies like circuit boards, move up a level to boxes or LRUs, line replaceable units. So these are, full electronics boxes, kind of like this example I have here. And then you can move up to like system level or subsystem level, where you have multiple components together, operating in unison. And eventually you get up to the fully integrated system, where it's perhaps an entire vehicle, or perhaps even a vehicle with associated, ground stations or other outside equipment. And in certain cases, you may have to do testing in the operational environment. So as an example, the military designs a new fighter airplane. They don't just test the airplane, see how fast it goes, how high it goes, and say, okay, it's good. Now, once they've proven out the aircraft, then they take it to an operational test phase where they identify how well does it work with, deploying weapons, and does it communicate with other aircraft, and can it be employed properly with the tactics. So there can be operational testing done beyond just the straight kind of mechanics of the engineering. And lastly, I wanted to end with talking about how important it is to make sure that you do proper documentation when it comes to testing. Now, we can probably do some other videos to explain how you go about documenting test plans, test objectives, test data collection and reporting. But really, those kinds of things are really important, because it doesn't take very long for the human mind to confuse and forget things. And having good documentation is invaluable for not just proving, from a verification standpoint that you satisfy your requirements, but all the time I'm going back to reports that were done years ago to go find out what we actually did, how we organized a test? What equipment did we use? What materials were in place? Because sometimes engineering changes even a couple of years down the line happen, and the question becomes, can I still trust the old test that we did, or do I have to repeat it with a different setup? And so having that documentation is invaluable for verifying it was done properly, making sure that it's a record for the actual verification that was done, but also it's really useful to go back to on a regular basis. Even if it's not you, if it's somebody else, it doesn't matter whether it's you or someone else. In a couple of years, you're never going to remember what exactly you did. You may feel like you can, but you usually go back and surprise yourself. So making sure that you do a good job of documenting what it is you're testing, why you're testing it, what you did, what data you got is really important. And I want to make sure to emphasize that, so that as you are becoming an engineer and growing up to become a lead, that you recognize that is an important part of being a good engineer, and that folks will recognize when you do a good job of documenting things properly. And that's all for today's video. Keep exploring, and we'll catch you on the next one.